Hi, I'm Cadet Grover Hoover, Company B1.
Hi, I'm Cadet Michael Etnier, Company F4.
Hi, I'm Cadet Robert Jenkins, Company F3.
Hi, I'm Cadet Zachary Royal, Company D4.
Hi, I'm Jacob Weiss, Company B4.
And we are Team IGVC.
Hello, my name is Zachary Royal, and welcome to the Intelligent Ground Vehicle Competition Sprint 4 review. Our goal for this sprint was to be able to run IGVC through a test obstacle course where it would need to be able to detect and treat white lines as obstacles so that it moved within a lane, navigated to a list of GPS waypoints given in a .csv file, and avoid obstacles in its path. Given our 5 group members and 13 lessons, the scope for this project was 178.5 hours. Overall, while many portions of our sprint tasks worked individually, when trying to integrate them to work together, we met several obstacles that proved to be large time sinks, and ultimately, we were unable to get past the integration portion to test everything working in conjunction and meet our sprint goal. The Sprint 4 deliverables consisted of the following: a functioning GPS navigation and simulation, the same software working in real life, increased GPS accuracy, functioning white line detection and lane following, as well as a fixed network detection allowing us to connect and SSH into IGVC without the slowdown we've been experiencing lately. Here are Sprint 4 tasks for this sprint. The total estimated time ended up consisting of 178.5 hours with an actual time of 162.5 hours. The actual tasks were waypoint navigation, implementing a 2016 lane following solution to fix the navigation system, conduct GPS system tests, make a rough draft of the paper, configure virtual Velodyne sensors and vision sensors, design an outdoor obstacle course that we could use later, and implement dynamic reconfiguration for the vision. Here's our burn down for the chart. Again, it was approximately estimated to be 178.5 hours, and we ended up doing an actual time of 162.5 hours. Here's our product roadmap. Overall, in the next sprint, we need to start looking for some major feature additions of flag detection, improving the waypoint navigation and obstacle avoidance, because right now it can get stuck in a loop where it loses some time, as well as beginning to test our outdoor qualification capabilities once everything has been implemented. This is Zachary Royal, and for my portion of the sprint, I sought to fix and integrate GPS waypoint navigation. GPS navigation was an important piece of reaching our sprint goal and ultimately passing the initial qualification course. The first step in this process was to utilize a Python executable which would subscribe to a series of topics that provided IGVC's location both in GPS and in local time frame. Here you are seeing the results of that conducted within simulation. Then it takes a list of waypoints from that CSV file and translates them into positions on the local map that IGVC can then travel to. Finally, it should publish these points as navigation goals. After writing code to fix this issue, I tested it rigorously in simulation, and while the vision solution was being implemented on IGVC. After being relatively satisfied with the test results, and in which the simulated IGVC could travel over 30 waypoints autonomously, I ran into difficulty attempting to integrate it with the vision solution on IGVC and was ultimately unsuccessful in getting it to work on the hardware. The integration piece will be very important in the next sprint.
Good morning, my name is Cadet Etnier. I will be going over my part of the sprint 4. Just general, the IGVC sprint goal. The goal of the sprint was to run IGVC through a test obstacle course where it will be able to perform rudimentary line following waypoint navigation between several GPS points and obstacle avoidance. So fitting into that, my part of the sprint, my sprint goal individually was to conduct tests on the GPS system to determine whether or not the CNS 5000 or the XNs was the better sensor for IGVC to use. So on the screen right now are one of the 2 tests I did. 2 tests. The first test was to see if the CNS moved out of PPP mode, the precise point positioning mode, which allows a higher accuracy of lat long at max speed. It did not move out of that at max speed, so we continued to the next test, which was to compare the XNs and the CNS. So if you look on the screen, this is one of 2 tests that we did for this. and as you can see, the blue, which is the XNs, and the green, which is the CNS, the blue had a lot larger variance as each lap progressed, meaning that it slipped and it wasn't as consistent as the XNs, which you can see is a pretty solid green line. Zooming in on that same image, you can tell that the same thing happens. The CNS is much more consistent with data. We did the same test again twice. Same story here. This one's a little bigger of a difference, and you can see the blue again, which is the XNs, is a lot more variance in the points that it was collecting when compared to the CNS, which is basically the box that we drove for every 3 laps. Here's zoomed in again. So then going from there, we look over. Here's the numerical comparing we did. So this is the first test, and you can see right here there's about a max difference of 35 centimeters roughly between what the XNs is giving and what the CNS is giving. So that means that there's about that much of a difference. And you go to the other test, we're at about 87. So from this test, we concluded that the CNS was much better for Iggy than the XNs. And then I went ahead and installed the CNS back into Iggy, and also made some minor hardware repairs that were broken from the competition last year. That concludes my part of the sprint. Thank you.
Hello, my name is Cadet Robert Jenkins, and one of the things I was responsible for during this sprint was creating a network that could adequately handle all of the different devices that are attached to Iggy. After thoroughly inspecting all the different devices, this is the network diagram that I will use to implement the network on top of Iggy. After configuring the network, I ran a series of tests to see how well the network was handling the different devices. I ran several different TCP dump commands on both network interfaces with different combinations of devices being used to see how well the network would hold up. From my tests, I was able to deduce that our network is able to handle all the different devices working simultaneously, but there is a lag. During my next sprint, I will be working on how to reduce this lag. During the back half of the sprint, I worked on creating a CAD-based model for the simulation that I was working on in previous sprints. In this video, you can see the beginning stages of a more realistic model instead of the Jackal robot we were using in our simulation. In the upcoming sprint, I will continue work on this model in order to implement a more aesthetically pleasing model into the simulation piece.
Hello, my name is Cadet Jacob Weiss, and for this sprint, I was responsible for the lane following portion of our sprint goal. Accomplishing this portion of the sprint goal required working with Cadet Jenkins in order to reconfigure Iggy's local network to allow the Jetson TK1 board to run alongside the rest of Iggy and the Velodyne LiDAR. I also implemented portions of the 2016 Capstone Team's vision solution to improve our line detection ability. Full integration with Iggy also required modifying Iggy's main launch file, transforms, and local cost map sources. Although the weather kept us from testing Iggy on an outdoor obstacle course, we were able to demonstrate Iggy's autonomous lane following ability indoors, completing the lane following portion of our sprint goal.
For our final reflection, we have some potential recommendations for Sprint 5. We're going to continue to work on the autonomous movement portion of Iggy as we start to prepare for passing a test obstacle qualification course. So we're going to continue to work on GPS waypoint navigation, improving our obstacle avoidance recovery behavior, and improving the white line detection under different types of light so that it can actually function outdoors, as right now we've only tested it indoors.